My final project report for Esys2. I ended up just doing this whole problem ahead of time because there was no way I could fit this whole thing in like 5 minutes, maybe even under 10 minutes. So this is a delta to a, or I'm sorry, this is a Y to a Y circuit. So it's going to be fairly simple. You're going to start with your 208. This was given by the problem, and so everything is just going to be minus 120 degrees in phase. And then on the other side, this is a balanced circuit, and actually for number 17, these resistors were all 0. So pretty simple. And then to start with, it's giving us a 1 kilo ohm resistance or impedance, if you will, for these numbers. So fairly simple. We're going to start, like I said, by putting these voltages. They're just 120 degrees out of phase with each other. And so we can put that into the rectangular form as well, just to make sure we have everything accounted for. And then if you'll notice, this and this is a node, and so going through the whole top and bottom, and that'll be equal to this. And oops, sorry, this is the C side. This and this, since A and B and A and B. Oh, I don't know why these numbers are swapped. This should be B and this should be C. Sorry, the letters. Yeah, it doesn't matter because all the impedances are equal. Okay, cool. I was making sure my notation didn't just get all messed up, because that's obviously not correct. So yeah, so the VAB is going to be VAN minus VBN. VBC is VBN minus VCN, and that's just basically by following the different branches. And that's going to be equal to the other side, just, looking off of the nodes. So easy enough. And then to find the impedances, if you know this voltage between here and here, I'm sorry, if you know this voltage between here and here, which is going to be equal to this voltage, and you know this, if these voltages are the same and you have an impedance, you can find a current going through here, and you'll notice that the current just goes straight into there. There's no branching off or anything like that, so it's just going to be it's going to be the same current. So that'll give you your line currents, which is what we find here. These are your line currents. And that's actually all the question was asking for, because the line voltage is going to be the same. The phase voltage going through the whole thing we've already accounted for, and now we have the line currents. If you wanted to find the current through here, theoretically you could, but I don't think it's really necessary. If you've got the current going into here and the current going into here, I mean, I don't know what you would need the total current for. And you have the currents going into each of these because they're equal to this. Like this is IB. So if you want to calculate power on this side, you want to calculate power on this side, you have all the equations that you need to. So the second one was with a different impedance. You're going to follow all the same steps. The only difference is when you're trying to find your line currents, you're going to have a different impedance there. And they're highlighted because of how I did my verification. Similarly, you do the part C was another additional impedance. So easy enough. And then you could see I did down here, I did the total power absorbed by the impedance. This was, it should be noted, with the plus 48J. And so these calculations were done so that I could do my verification. And so the verification, I transferred everything into a delta to delta. So if you'll keep in mind, these were the AN, BN, and CN voltages. Well, we took the AN minus BN, gave us VAB, right? Well, VA to B. So this is going to be equal to what we found for our VAB voltage. And the one nice thing with a delta function is this and this. Oh, look at that. A, B. Perfect. So there's your A to B voltage. Additionally, you have to change this impedance, because this was the impedance from the Y function, and it's not the same thing as it would be for a delta function. So here you have that calculation. Technically, this is like ZA, ZB, and then this is like ZA, ZC, and then this is like ZB, ZC, and this is like over ZA squared, and that would be the new, impedance for this A to B branch or something, right? But because it's a balanced circuit, they're all the same. So it's just going to be the same value squared plus the same value squared over the initial value. So that's going to give you this impedance for all three of these values. And so then you have the voltage A to B, and you have an impedance. So you can find the current A to B, this value, this value, this value, right here, which is going to be useful, because then in order to find your line currents, you can do some KCL. So if you have IBC, IAB, and this is your IB, then you can do some KCL. Now that line that I was just talking about right there, this KCL is this one right here. And so you can do your subtractions, and if you'll take a look, this value is actually the same that we had up earlier in our problem up here. I mean, we're off by minimal numbers. There's some rounding errors. And so then we can do, this is part of the verification, so we can do the total power absorbed again, because total power should be 0, right? Total power absorbed. But if we do the power absorbed by the impedance, that should tell us that our circuits are equal. So when you do the same thing where you use the I times I, or the initial I times the I conjugate, which gives you the magnitude of I squared, times the balanced impedance, you can get these values. And it turns out that these values are going to match what we had earlier, which shows that you did in fact have a verified problem. So, thank you very much.